Sure. Cheers.
Very good morning, ladies and gentlemen. A very warm and cheerful welcome to the day 3 of Qiskit Fall Fest 2025. And a very warm welcome to all our respected faculty members, dignitaries, guests, and the ever enthusiastic participants, of course. It's a brand new morning filled with fresh energy, sharper curiosity, and that some spark of innovation that has carried us through this incredible fest. Each day has unfolded, hopefully, a new dimension of learning, and today promises to be another exciting stride into the future of quantum learning. And before we begin, let me give you a quick glance at today's power packed schedule. We'll be starting our morning with a workshop session led by Dr. Jnana Yalla, CTO of DataTeach.ai, and a quantum machine learning and hybrid algorithm researcher. He will be guiding us through the concepts of quantum computing and quantum circuit compilation, continuing the wonderful learning experience we began yesterday. Following that, we'll have an in person guest lecture on quantum circuit compilation by Ms. Janani ma'am, quantum engineer at IBM Quantum Research, Bangalore, an expert known for her practical approach to quantum research and innovation. Then you'll be having a refreshing lunch break. Post lunch, we'll have the honor of hearing from Dr. V. Bhujangrao, former NSTL director, who will share his deep insights and experience from the scientific and defense research domain. And to conclude our exciting day, we'll have a virtual guest lecture by Professor Elias F. Combero, full professor at the University of Oviedo, Spain, and former member of CERN, speaking on quantum machine learning and its applications, a truly global perspective to end the day on a high note. So, yes, day 3 is completely packed with knowledge, innovation, and inspiration from some of the brightest minds in the quantum world. Yesterday's exploration introduced us to the fascinating world of quantum computing, from logic and classical concepts to the mysteries of qubits and superposition. And now, without any further ado, let's begin our first session of the day, the workshop session on quantum computing led by Dr. Jnana Yalla. So, participants, get ready to open your minds, tune in with curiosity, and immerse yourselves in this journey of quantum discovery. Let's welcome Dr. Jnana Yalla with a huge round of applause as we kickstart day 3 of Qiskit Fall Fest 2025.
Kuch- Good morning, everyone. I hope I'm audible. Yeah, cool. I'm audible. Nice. Okay. So, yes. Um, just wait a minute. Yeah. Okay. So, yeah, first of all, again, a very good morning to everyone. I'm Jnana Yalla, and yeah, as you already know, yesterday itself we started our session. So, yes, in today's session, I'll be going forward with some more like concepts in quantum computing, or yeah, quantum computing technically. So we'll be starting with some of the logics of quantum physics, like even more logics of quantum physics, which is very useful for quantum computing and quantum circuits and all this stuff. Okay, so yesterday we mostly had a session on something like why quantum, what is quantum, and how we can, why exactly do we need quantum, and some of the base states, like some of the basics of why quantum and how quantum works, technically to speak. Now, in today's session, first we'll be starting with some of the mathematical concepts, like which are exactly required only for quantum computations and stuff. And then, with the help of those logics, we will try to establish quantum circuits and quantum gates and how an exact quantum computation will happen. Meaning, completely converging or completely going to quantum computing from our quantum physics or quantum mechanics. Okay, so that will be the basic deal of today's workshop and today's concept. That's the basic gist of it. And in order to address some of the like queries of yesterday, I like to say, like, if you want to learn quantum computing, or if you want to be like a quantum physicist, or no, not exactly like a quantum physicist, but more like a quantum computing scientist or someone, it is not mandatory for you to be a pro physics guy. Okay, it is not mandatory. That depends on the thing which you are actually going. For example, if you want to be a quantum scientist for quantum materials or quantum sensing, at that time you need to have huge physics knowledge. Why? Because you will be dealing with materials. Materials have a lot of properties and you need to know everything. Other, if I want to be like a quantum machine learning engineer or quantum machine learning scientist, I don't need to, keep my mind that much on quantum materials. Okay, so that's why I don't need that much knowledge on quantum, materials or material properties, thermal properties, and all those stuff. Other, if you want to go to quantum communications, you need to have huge mathematical knowledge on how your actual communications and protocols work. For all these things, it is not mandatory that you should be a pro in physics. Pro in physics meaning you know magnets, you know electrics, you know kinematics, you know nuclear physics, should know everything. But it's not mandatory. Okay, it is not mandatory to be a quantum scientist. Okay, so that's a basic thing which I want to tell to everyone. You should focus on the aspects which you want to go through. For example, quantum machine learning engineer concentrate more on optimization or Hamiltonian equations or energy equations and stuff like that. Quantum communication and quantum cryptography focus more on mathematics behind communications, networks, protocols, signals, waves, and those concepts. So it works in that way. You don't need to be a complete physicist guy. Okay, that's the first thing which I want to tell. Just keep this in your mind so that you don't need to lose motivation. Else, yesterday I just listened this a lot or heard this a lot. Most of the people came and they were like, "I am not a physics guy, or I am not into physics. Then how can I be this quantum guy?" At that time, I answered the same question. So that might be there for everyone or most of the people sitting here. So that's the reason I'm just addressing it. Okay, now you don't need to be a pro physicist in order to be a quantum guy. Now, now let's actually dive into today's session. What was the last topic of yesterday? I forgot. That's why I'm asking. Dot product, huh? Okay, I was just kidding. I remember. Now, so the last topic was yesterday is we dealt with something called as a dot product. Okay, so that dot product can look like this, approximately. Not approximately, it's known as an inner product, which is nothing but the complex version of dot product. So this is the thing which we've seen in the yesterday session, the last one. And I also told you what an inner product gives. So what is the value of an inner product? How it will be there? It will be like what? A1 star B1 plus A2 star B2 plus so on up to AN star BN. NO, MO, AO, BO, CO మీ ఇష్టమైన వాడుకోవచ్చు ప్రాబ్లం ఏం లేదు. So this is the inner product. Okay, and this inner product gives me a value which is known as a complex scalar. That's also an important thing which you need to remember, which I mentioned as well. Complex scalar. This gives a complex scalar. Okay. Okay, this gives a complex scalar. Now, now let's actually take care about this in a more detailed way. So, when I was mentioning about Hilbert space yesterday, I mentioned one important thing. What is the concept which I mentioned? First thing is it's complete. Okay. Second thing is that it has inner product norms. Okay. Meaning every vector in a Hilbert space has an inner product. Okay. That's the first thing. Every vector in a Hilbert space has inner product, meaning we can find the inner product of the stuff. And one more important thing is the norm, the concept called as norm. Okay, because it has inner vector norms. NORM, norm, inner vector norms. So what exactly is this norm? So from here we're going to start the new concepts of today's session. So it already this we have already completed this yesterday itself. So from today it's from the norm. So what exactly is norm? Now, sorry, okay, my bad. Which is I just need to get habituated. Cool. So what exactly is a norm? For example, let's take a vector. Okay, let's take any vector. Like normal. Don't be like quantum or whatever. Just a normal vector. Normal kinematics lo vector because just a normal vector. Let us consider a vector called A. So how a vector looks like? Let us consider three-dimensional vector. ఎలా ఉంటది అసలు? So approximately I can take like a1x plus a2y plus a3c. Okay, so I'll just keep a caps on everything. If you want, you can keep I cap, J cap, K cap as well. You wish completely all right. I just want to determine it by the coordinates. So this is how a normal vector looks like. A basic vector. This is a vector. If I say norm of this vector, what is the meaning behind it? Okay, norm light. What is the magnitude of this vector? Remember magnitude? Kinematics? Yes, that one only. So, so you will define magnitude of a vector like this. Yes, I hope, right? This is how we define the magnitude of a vector, which is equal to root of a1 square plus a2 square plus a3 square. Right? This is the thing which we did, the magnitude of a vector. What exactly is this magnitude determine? What exactly does this determine? We know about magnitude of a vector. Cool. What exactly does this mean? If I say the magnitude of this vector is phi equal to phi and theta, what is the meaning behind it? Correct. The length. Yes. So this determines the this determines the length. So the magnitude of a vector always determines something called as the length of the vector. The length of the vector. Now, similarly, the same thing. For example, if you take the magnitude of a quantum state. So in yesterday's session, I have clearly mentioned that quantum states, everything exists in where? Where does they exist? It is exists in Hilbert space. Okay. So Hilbert space, may we have vectors. That's the thing that n-dimensional vectors we have. Okay. So if you take the magnitude of a quantum state, meaning when you take the magnitude, I'm just writing a mag. Don't worry or anything. I'm just writing as mag. Okay. So when you take a magnitude of the real meaning is if you take a magnitude of a vector in a Hilbert space. Okay. The real meaning is if you take a magnitude of a vector in Hilbert space, I will determine the Hilbert space like this. Okay. H పక్కన ఒక line. Hilbert space. Okay. So a weird H with a line. Okay. If you take the magnitude of a vector in a Hilbert space, I will call it as norm. Simple thing. Okay. Very straightforward. Don't need to think that much. Direct one. For a classical vector, meaning a vector in a coordinate space, later let us consider a vector in Minkowski space or whatever, a vector's length is determined by magnitude. Similarly, if you take the magnitude of a vector which exists in a Hilbert space, meaning it can be complex as well. Okay. So Hilbert space may you have complex vectors. That's what we see in a star. Okay. So if you take the magnitude of a vector in a Hilbert space, then I will call it as a norm, simply to put. Okay. That's a basic deal behind a norm. Now, how this norm can be exactly? Let me do some practicals. No. Okay. Okay. So how this norm looks like? Same deal. There's no that difference or something. Directly it looks like the same thing. Okay. So you don't need to think anything. Now let us directly dive into quantum. Now, if I'm talking about the quantum states, okay, let us consider a state called psi. If you take this thing, if you take the inner product, or if you take the inner product of a quantum state, and if you just keep this is known as the norm of the quantum state. Okay, and the norm of the quantum state is always equal to 1. Why it always equals to 1? Because it is probabilities. Okay, if you take each and every coefficient of a state, quantum state, they determine the probabilities. The square of them determine the probabilities. That's what we saw in yesterday's session. Remember? How does this looks like? Yes, correct. Alpha 0 plus beta 1. Alpha and beta determines what? They determine amplitude. Okay, they determine amplitude. What is probability? Alpha square determines probability and beta square determines probability. Now, can you tell me why this thing is equal to 1? Why? Because if you take a dot magnitude, let's go back to the magnitude. Forget about norm. Let's go back to the magnitude. If you take the magnitude, you're simply doing this thing, right? If you take the magnitude, we are simply doing this particular operation. What is that operation? It's nothing but, let us consider, it's nothing but this one, right? For example, a square plus b square plus so on. Is this the operation we are doing for magnitude? Right? Now do the same thing for this one, for a quantum state. It will be like alpha square plus beta square plus so on. Like how many states it has, that much it can be. Now let us consider only alpha naught plus beta 1. For alpha square plus beta square, that's it. What is alpha square plus beta square? What is the value of alpha square plus beta square? It's a sum of probabilities. Alpha square is a probability, beta square is a probability. So sum of probabilities is always equal to 1. So root of 1, yanta 1. Okay, that's a simple deal, and that's why the norm of a quantum state, the norm of a quantum state is always equal to 1. This one. Okay, now let us not consider the same quantum state. Let us consider different quantum states. Let's go with the different quantum states. Two quantum states. Now how will it be? So everyone understood till here how the norm of a quantum state will become 1 just because of the probabilities. Just because of the concept of probabilities, it will be equal to 1. Just add them up, it will be 1. Now, now let us consider another thing. That is about your different quantum states. Let us consider different. Let us consider two quantum states. First quantum state looks like my psi, sorry, and the second quantum state looks like my phi. Okay, let's consider two quantum states. I don't want to derive the formula. If you want to derive, you can derive. Like for example, now if I take the inner product of this one, how will it be? It will be something like this. So what will it be? The same formula which you write. So it will be something like this: 1 star into this one plus so on up to n star psi n. Okay, it will be like the same thing. Okay, this is the inner product. Now if you want to do the norm of this one or something, you will be simply be like square it off. Okay, not a problem, completely all right. But okay, so this is not a formula, but yeah, but that's the main deal of the norm. Now let us directly consider how, what or not how, what does this determine in a quantum state. Quantum states, we are talking about quantum states, that's why we are having the inner product, else we can normally take the magnitude itself, not a problem. Now, when you're dealing with the quantum state, if both the states are same, then it is equal to 1, which we've seen right now, right? Probabilities untai as multiply as so 1. Okay? If you take two quantum states, like different quantum states, then the probabilities of this one is different and this one is different. Yes or no? The probabilities of two of them will be different, right? One will give rise to its own probabilities, the second one will give rise to its own probability. So both are different. In that case, what does this determine? Simple, just have an idea of it. It determines this guy. What does it determine until? See here properly. When I take this, when I'm considering a square, okay, this determines something known as the probability of observing, or the probability of psi changing to phi. That's a simple deal. Okay. The probability of the quantum state psi changing to the quantum state phi. So that is the meaning behind this one. Okay. A simple deal. Just keep that in your mind. For example, if you have two quantum states, phi and a psi, this formula determines this particular thing. Remember this thing exactly. If you change them, the formula will be different and it will be gone. That's why write it perfectly or keep this in your mind perfectly. The deal goes like this. For example, when you take phi slash of psi, the meaning is conversion of psi to phi. Okay. The probability of state psi changing to state phi. That is the value of this one. Got it? Understood? This is a simple deal behind it. Got it, everyone? That's it. Not even any case. Now, if you want to actually find the measure of this one, I want to find the measure, bro. Because if we are having the same quantum state equal to 1, okay, measure I pinned, pixel item. Now, if you are having multiple quantum states, I have two quantum states here, and I'm saying that if I find this actual value, the meaning is that I am finding the probability of the psi state changing to phi. Yes or no? I am finding the probability. But what is the actual measure? How can I find that? Same old rules and same old stuff only. But it is a different concept. Okay? Concept and theory is same. Okay, the entire theory is same and entire stuff is same. But the only thing which is different is the actual measurement, the actual values. So what is that, Ante? That's where your new rule comes into play, which is known as bond rule. We will call it as bond rule. Okay, these are very important topics. Now, yes, this is known as a bond rule. So normally we found the inner product of two quantum states. Yeah. So normally we found the inner product of same quantum state. We got one. Very cool. We found the inner product of two quantum states, and we got to know that that is a probability of the state changing from psi to phi. But what is the actual value? How can I find the actual value? The finding of the actual value is bond rule. Now, before actually going to bond rule, you should know something about measurement. There is something called as measurement. Just keep a hashtag measurement. This measurement is completely different from the measurement which we actually see when we are dealing with physical computing. Hello? Yeah, okay, sorry. So now, how it is exactly different? Simple deal. In yesterday's session, yeah, in yesterday's session, I have clearly mentioned about something called as if you measure a superposition state, it will be decomposed to one of the base state. Remember? Did anyone of you try to ask me how? You guys simply are concerned like, okay, that's it. End of discussion. Okay, normally that's it. End of discussion only. Why? Because it's a physics property. But yeah, normally physics means we can't say how. We simply can define them in mathematical way. That's it. Okay, if I drop this, it will fall down. How it falls down, I can't say, but I can define it. It's a physical property. It's gravity. I know it's gravity, and I can write the gravity in a mathematical ways. Similarly, this measurement concept, where a superposition state, when measuring, decomposes to one of the base state, can be defined in a physics way, or I can say quantum mechanical way, mathematical way, or whatever. Okay, and that is the entire deal behind it, and that's where your bond rule and your measurement theorem, everything comes into play. Okay, now, so in this measurement concept, we are actually seeing how measuring a quantum state. Now, just listen this. One more thing before actually going to measurement, just keep this in your mind. పక్కన బాక్స్ చేసుకుని రాసుకోండి కావస్తే if you want. Every quantum state, we will represent it in a form of superposition state only. Now you may ask, like, if I represent it in the form of superposition state, so every qubit should be 0 and 1, right? But in yesterday's session, I have mentioned one thing. It can be 0, it can be 1, and it can be 0 and 1, I told. Okay. Now, if that is true, then how is this one possible? Simple. It all deals with a what can I say? That equation, that qubit equation. Every quantum state, I will define it in this way only. Every quantum state I will define in this way only. Okay, I won't change it. I will define in this way only. But if it is a zero state, if it is state zero, I will be like beta equal to 0. That's it. And if it is in one state, I will simply be like, I'll make if 0. I'll simply make alpha equal to 0 if it is one state. That's it. Okay. But when I'm actually defining or when I'm actually calculating in at that point of time, I will definitely define it in this way. That's a rule. Every quantum computation or every property or everything, I will definitely define it in this way only. Okay. So in yesterday's session, I have mentioned it can be zero state. So I cannot define like this. No, I cannot do it. Okay. So if I want to define, I will write like this and I will make beta equal to 0. If I want it to be a what can I say, zeroth state. If I want it to be in a zeroth state, I will write it like this and then I will make beta equal to 0. Getting the point? So that's the main thing. So keep this in your mind. It is not like You can make like direct the psi equal to 0. No, you cannot do that. Okay, every qubit you should represent it in a superposition format only. And if it is in a 0 state, just make beta equal to 0. If it is in 1 state, just make alpha equal to 0. That's it. Okay, but defining should be in, what can I say this as? Superposition state only. Got it? That's the main deal. Now we can actually go to measurement. Yes. So now we can actually go to measurement. Now, so let's go back to the yesterday's thing only. So I hope you guys wrote it in a side top left box or top right box. Now let's come to the actual stuff. Now, in yesterday's session, I have mentioned one thing. Let me just revise it off. I already revised it right now, like 10 minutes back, but again, I will say it once more. That is, when you measure a quantum state, this will be decomposed into, this arrow mark signifies decomposed, let us consider, into one of basis state or one of the base state. Okay, basis state, they are different words. Okay, let us consider like this. This is the entire thing. How? Like, not like how I can just show it. Very simple. Okay, very direct way. Whenever we measure something, the process of measurement, like if you're measuring something, that means what you're doing, you are doing some operation out there, yes or no, if you want to measure something. So let's go to the scroll in the experiment. So you want to measure the state of the cat, meaning you want to see if the cat is alive or dead. So just by sitting, can you say like it's alive or it's dead? No, you are going and you're opening the box, meaning you are doing some work. Okay. Similarly, if you want to take something, if you want to capture something, if you want to measure something, like for example, if I ask you the capacity of water inside this bottle, you'll pour it in a funnel or something and then you'll see the markings and then you'll measure it. Okay. So you are doing some operation out there. Okay. And when it comes to quantum, the measure, that measurement, we call it as an observable or an observer or anything. Use that word. Anma. Whenever Yeah. So whenever I mention something about measurement or something like that, sorry, whenever I mention measurement, it is that I am talking about something known as an observer, or I can say excuse me, guys, just a sec. Yes, okay. I hope this is okay. Yeah, cool. So, whenever I talk about measurement, I am talking about something known as an observer or observable. Okay, I can simply consider it like this. So, now, before even going into this in more detailed way, let us see about one more case which happened in Young's slit experiment. Okay, so that's actually kind of cool. So, that's why I will just say it. And I did not say it yesterday just because I want to explain with the concept of measurement. Now, when I talk about measurement, I told that it is an observer or an observable, right? Until we are doing some action, the action which we are doing in order to exactly. Okay. Now, now the deal goes like this. Yesterday, you guys remember Young's double slit experiment, right? When you had a single slit, what happened? You saw a straight pattern. So, which was like this, saying that electron is a what particle or wave? Particle. Now, when you kept a double slit, when you kept a double slit, what happened? You saw something known as an which pattern? What's the pattern called? inference. Okay, it's known as interference pattern actually. So yesterday did I mention as inference? Huh? Okay, this is known as interference pattern. So my bad actually. Now, so it's in okay. So what is this interference pattern? Simple. The middle guy or the center guy will be very bright, followed by some gap and a semi-bright gap and even small light and it small. Same goes here. Same pattern follows here. This is very bright. This is kind. This is also like small bright and last one is very thin. Okay, like very dim kind of thing. Okay. So this is how it actually works and this is known as an interference pattern. Okay. And an interference pattern is only observed when we are having the input in the form of a wave. Okay. An interference pattern is only observed when we have the input in the form of a wave, thereby stating that electron is a wave. Okay. So if there is only a single slit, it behaves like a particle. But if you are having a double slit, it behaves like a wave. Okay. Now what this scientists think ante, something cannot be in two of the states, or something cannot be like two of them. It can be like only one thing, right? So they decided to see how it actually is. Okay. Like they decided to measure it, simply to put, they wanted to see how it actually is. Like because normally when I did this experiment, I did not see the electron. I am simply observing the screen to determine how it is actually. But as in first case, it determined like a particle, and in second case, it determined like a wave. The scientists got confused and they wanted to see how it actually is. Okay, I wanted to simply see how it is actually behaving. So for that reason, in the third round, what did they do is in the third round or in a third iteration, they did something like this. Same double slit, not a problem. And they attached two cameras. One camera in the first slit and one more camera in the second slit. So this is not a gun, that's a camera. Okay, let us consider that's a camera. Okay, and the same experiment, same gun here, and shoot the electrons. Okay, understood? So they simply attach two cameras at the end of two slits to see how it is actually is. Okay, in order to see how it actually is, they attach two cameras. Now they observed in the screen only two thick lines. They did not observe the interference pattern. So what did they observe? They observed something like this. That's it. So simply saying that electron is a what at this case? Electron became a particle. So this is the actual deal. So what happened here when I did not observe it? That is in the second case. I did not observe it, right? So it became a what can I say? It behaved like a wave. Completely all right. I got an interference pattern. So I got to know that it is a wave. Okay. Completely all right. Now, when I actually wanted to see how it actually is, I kept two cameras at the end of the slits and I repeated the same experiment and I got this pattern telling that electron is behaving like a particle but not a wave. So scientists got confused and that's where here where they told that when we did not keep the camera, it came as an interference pattern. When we kept a camera, meaning technically to speak, when we are observing the particle, it is behaving like a sorry, when we are observing that electron, it behaved like a particle. Meaning this concept called as observation or observable or observing or measuring is influencing the state of the quantum. So I'll just write like this because I don't know how the state looks like. So I kept like a particle and I kept like this, which determines a particle and wave. Okay, so like two of them kalapunnattu. Okay, so meaning in the first case, it behaved like a particle, completely all right. In the second case, it behaved like a wave, and in the third case, it behaved like a particle again. Meaning the measurement what I'm doing. So the main like the observation is equal to measurement. That's what I told now. So the measurement which we are actually doing is influencing the state of the quantum. Yes or no? Are you guys getting the point? Why? Because electron is a subatomic particle, meaning electron is a quantum state. Okay. And when I'm observing that one, like when I'm measuring that one, that is influencing state of the quantum. Are you guys able to get this one? This one point? So that's why they got to know that observation or measurement has a direct influence in the quantum state. Adhavenda? So that's why I told, like when you measure a superposition state, it will come to one of the base states. So that's the entire deal behind it. Got it? Now, how it actually is happening? What is the mathematical definition of this one? Normally, this is the theory. I hope you guys understood the theory, right? You don't observe it, it will be in a superposition state. But when you observe it, it will simply decompose to one of the base state. Okay? Same two examples. One example is a Schrodinger cat. Second example is this Young's double slit experiment. Okay? You don't observe the electron, it acts like a wave or it acts like whatever it is. But when you observe it, it is decomposing into one of the guy. Are you getting the point? So that's the deal. So when you're measuring it before itself or when you're measuring a quantum state, it decomposes. Meaning measurement has a direct influence on the quantum. Now let's go to the mathematics. How I can define it? Simple. Every measurement. So what happened after the third result of YDSC is that scientists got to understand, like if I am observing it, then it is influencing the quantum state. So what exactly is influencing the quantum state? The measurement. Okay. So meaning is when I'm saying that I keep a camera, okay, or I'm seeing or looking at it, it is decomposing my quantum state. Okay. So what exactly is there when we are measuring that it is decomposing the quantum state? That's a doubt which came into play. Okay. I can't simply say, like, for example, if I look at this bottle falls down, let us consider. That means there is something in my eyes which is influencing the behavior of this thing. Yes or no? Are you getting the point? Let us consider, I just looked at the bottle falls down. The meaning goes like this. There is something in my eyes which is influencing the bottle to fall down. So the same thing the scientists also got doubt. Like they just got this doubt. Like what is there in the measurement which is influencing the state of the quantum? Influencing ante asala what is applying on that particular thing? What is influencing its behavior? What is actually happening? And they got to know that when you keep a camera, obviously it takes the pic, it records. Kada? Recording means what? How I can see the part, like why I'm able to see you people, or how I can see you because of correct answer. What is that? Because of light. So I am able to observe something because of light. So if you really see, light also behaves like a light is also like a subatomic guy. Okay, and it also behaves like two things, wave and a particle. Remember? So light can be determined as a wave and it can also be determined as a particle. Okay. So what the scientists taught is when I'm actually measuring something, the state is getting decomposed. The quantum state is getting decomposed. Meaning something in my measurement is affecting the quantum state. And they taught like the what can I say that the camera is there now. The camera one is emitting certain photons which is actually influencing the quantum state. That's what they got to know. That's what they taught in the first place. Okay, that's a one of the deal. Now, similarly, if you take any sort of measurement, okay, when I'm talking about any sort of measurement, I can define or I can write my measurement as something called as a Hermitian operator. I can define my measurement as something known as a Hermitian operator. Meaning, when I'm saying that I am measuring something or when I'm observing something, it is a physical entity. Meaning, this can be a light, maybe a pulse, or a energy state or energy pulse or whatever it is, or gravity or noise or whatever stuff it can be. Whatever, you can just pull whatever stuff, any physics quantity you can keep. Like for example, these all are used when you're dealing with different type of quantum computers, like superconducting qubits or superconducting computers may we will influence with electricity and stuff. So if you're using the magnetic based things, you will be using with magnetism, the ferromagnetism and stuff like that. So light, you will be using the energy pulses, the laser pulses and stuff. So all defines on that particular thing. Okay. Depending on the type of computer, or depending on the type of quantum computer which you're using, all these things will be changed or all these measurements will be taken care of. Okay. So that's the entire deal, which is actually influencing the stuff. So this measurement is actually influencing, and I can define that measurement as a physical entity. It can be anything. Electricity, gani, pulse, light, sound, noise, gravity, whatever it can be. Okay. And that physical measurement or that physical entity, I will define it like a Hermitian operator in a mathematical way. In mathematics, if I want to define something in mathematical way, I will define it in the form of a Hermitian operator. So what is this Hermitian? So, do you guys listen or heard about Hermitian guys before? Hermitian ante enti? If a matrix A equal to A dagger or is it equal to A star? I will call it as a Hermitian matrix. Okay. If a matrix is Hermitian, oh sorry, when now I can say a matrix is Hermitian if it is equal. Simply to put, there's a basic deal behind it. Okay, you don't need to think anything. That's a very basic deal behind it. Did the minds conjugate transpose? Okay, simple deal. You don't need to think about it that much, and that's your Hermitian bala. Now, okay, I mentioned okay, measurement equal to a physical operator, which is a Hermitian operator. So everything. Now you got to know one thing. Now, right now we're having two things. What is that? First thing is a quantum state, which we are actually going to measure, which is a superposition state, alpha naught, beta one, whatever. And second thing is the measurable A. Okay, which is known as okay, measurable A, which is a Hermitian operator. Okay. Now, how it actually influence? Very simple thing. First, I will say the definition or a direct definition. Just keep that in your mind directly. The definition goes like this. What is that, Ante? Whenever, whenever A is applied to in H. Okay, what is H? Hilbert space. Yes. So whenever you apply a measurable to a quantum state in a Hilbert space, simply to put a straightforward thing, this guy, the state will be projected to one of the eigenstates of A. Simple deal. Just this point is important. One of the. So whenever you're measuring or whenever you're applying a measurable A, measurable called as A, which is measurable, which is a Hermitian operator. Whenever you're applying that measurable A to a quantum state psi in a Hilbert space H, or in order to say very clearly, let us consider a single state, so it will be like C square. Now I can say that this psi state will be projected to one of the eigenstates of A. And this guy will be the one of the basis state I mentioned before. So this is approximately analogous to one of the base state. That's why the measurable thing, the outcome after a measurement will not be a superposition state. The outcome or the output of a measurement will be a measurable state. Got it? So that's a simple deal behind it. Understood? Very simple deal. So that's the reason why when you're measuring something, it will be decomposed to one of the base states. Okay. So in order to say it mathematical way, the bond rule I did not define it yet, right? So I defined the bond rule, but I did not write the expression. So the expression is very simple or very straightforward. Now, when I say eigenstate A, I can simply say like this: A AI equal to AI. Okay, which you already know, the eigenvalues, eigenvectors, you already know na, the same day. Meaning, this guy will be converted అని కాదు, but this guy can be transposed or this guy can be reflected in this way, where this is the simply to put the amplitude. And this is the eigenstate. AI is the eigenstate. And a vector A or the operator capital A can have many eigenstates, right? So any vector, I will give you a matrix. It can have any number of eigenstates, right? So similarly, this guy has a lot of eigenstates, out of which only one of the eigenstate is your actual answer. Got it? That's a basic deal behind it. And this AI is the amplitude of it. And if you take the AI square, it is nothing but the probability, which you already know, the quantum things, right? That's what I mentioned, right? Alpha is amplitude, alpha square is probability. The same deal. Now, how exactly it can be determined by bond rule? Ante very simple. If you're taking any state psi, I will write it like this. Okay. Now, if I say it has n states, I can write like this. Okay. Any state. For example, initially 2 base states, but I wrote like this. Let us consider it has n base states. At that time, I can determine like this. Meaning, I can write it like yes or no. Can I write in this way? Simple. Only 2 base states unte idi. Let us consider n states. Okay. For example, if you're having n states, it is like this. So, can I determine this n state in this way? Yes or no? Simply addition ko summation is petanta. That's it. I can determine in this way. Now, what is the probabilities? So, if I take these are the probabilities. Yes or no? Are you guys getting it? So why? Because when we have alpha naught plus beta 1, it's nothing but alpha square plus beta square equal to 1. Let us consider like that you are having 5. A1 square plus A2 square plus A3 square up to AN square equal to 1. So that's the same thing which I wrote here, which is the probabilities. Are you guys able to follow this one? Just a mathematical notations. That's it. Now, what I can say is, for example, when I want to mention it in an observable and some in that way, I can write like this actually. I can write the output state equal to summation of I equal to 1 to n, same thing, ai of ai square, ai vector. Okay. So what is phi? Let us consider when you're measuring a psi. So you are measuring it and it gives you phi. Let us consider like that. Okay. Okay, simple deal. Let us consider a very basic thing like this. So our entire concept is I am measuring psi, meaning I am measuring a quantum state psi with an operator A. Yes or no? So now when I am measuring a quantum state psi with an operator A, that will convert. Obviously, that will convert. Ice cube on the temperature event, it will be converted to water, right? Same thing. State keep a measurable, it will be converting. Let us consider the conversion is to phi state, psi to phi. Now, if you remember, what is this thing? What is this defined? కనిపిస్తుంది కదా? Okay, sorry. What is this defined? Okay, so it's my bad. I just need to. What is this defined? Probability of psi changing to phi. Okay, very simple deal, direct deal. Now, this is phi, right? Now, if I want to say that, now the bond rule comes into place. So the bond rule says that AI can be written as AI. That's it. Okay. So I can say AI can be written as AI, like AI inner product of psi, meaning the state or the inner product of psi converting to AI. Now I mentioned one more thing. AI is what? Amplitude. Exactly. It's an eigenvalue, or I can say it's an amplitude. Okay, that's what I mentioned before, right? Like top ఇక్కడ ఉంటది notes లో. So that is amplitude. So that's why I also mentioned this particular thing. Equal to 1 అని కూడా రాశాను. Why? Because amplitude square చేస్తే it's a probability that's equal to 1. Now AI is written as this thing according to Bond rule. AI can be written as this particular thing according to Bond rule. Now, oh sorry, it's I can write it like CI. CI. CI can be written as this particular thing in Bond rule. Now, okay. Now, if I'm mentioning the probability, it's nothing but CI square, right? So if I take CI square, I can write it like this as well, which is analogous to looking like this. So thereby, this gives a probability of psi giving an output AI. Got it? So that's a simple deal, and this is how the decomposition actually happens as per mathematics and stuff. Advainda. So anyway, this entire notes will be provided to you so that you can see all the stuff here and there, and you can just wrap. Okay. So yeah, I would like to conclude till here for this thing. So we'll be having one more thing later, like in after some time, I guess. So I will just conclude till here up to the measurement. So just take a revision and stuff like that. Cool. Okay. Thank you so much, everyone.
It is such an incredible session, sir. Thank you so much for such an insightful session. We have a standard to Dr. Janani for guiding us the fascinating world of quantum mechanics so clearly and very patiently. We started with the basics, and it was an amazing start to see that you don't need to be a physics expert to be a quantum enthusiast. It's just a curious mind itself. And we got to peek into the language of quantum mechanics, like the Bragg rotation and Mohs. But today made that really made sense. The most exciting part is understanding quantum states and superposition. How a state can exist as a mix of zero and one absolute measurement. And speaking of measurement, the experiment perfectly showed how observation itself changes what happens in the quantum world. That really made us stop and think for a while. Thank you, sir, for making such complex ideas feel accessible and fascinating. We really appreciate your time, patience, and the way you took the session. Let's give another big round of applause for the amazing session. Now, as we move forward, it's time to dive deeper into the fascinating realm of quantum circuit compilation, one of the most crucial and intellectually stimulating areas in quantum computing. And for that, I'd like to call upon Nikhil Teja, our lead organizer, to introduce the guest to you.
So, hello everybody. Once again, we're going to start another session. So, I'd like to introduce Ms. Janani. Ms. Janani is a highly accomplished professional who has been deeply involved in advancing quantum computing technologies and developing innovative approaches to solve. And we are truly privileged to have with us exceptional expert, Janani, a quantum engineer at IBM Quantum Research Bangalore. Beyond her technical expertise, she also enthusiastically building aspiring quantum levels and for the contribution to the broader quantum community through research, collaboration, and education initiatives. Our journey stands as an inspiration to all of us who are inspired to share the future through quantum innovation. So, with immense respect, let's welcome with studying a bias to deliver a message of quantum self-compilation.
Connect the HTML. Connect the HTML to and then start. Yeah, I keep to connect this. Hello. Um, Firstly, thank you so much for the warm welcome, Nikhil. The aspect ratio seems a bit off. Can we, for the presentation, can we just get it to come in the center or would you have a slide? Great. Um, Firstly, hi everyone. I'm so excited and thrilled to be here. This is probably one of the largest audiences that I've had the privilege of speaking to. And more than that, the past day that I've been here, I've been able to kind of feel the enthusiasm that all of you have for quantum computing. And as someone in the field, this is truly heartwarming for me to see. So, let's get started with the session. And I hope. You can take away from here and this fest and build forward and keep doing more quantum computing. So let's get started. uh, this will be okay. Yeah, I can actually do this. uh, yeah. Okay, let's get started. First, I want to set the tone for this talk. Okay, I want to recount the words that Dr. Venkata Subramaniam he told us. I'm from IBM, by the way. So when he first told us about the news that quantum computer is coming to Amravati, he used some specific words. He said, "The stars are aligning and the sky is the limit." So this is the replica of IBM Quantum System 2 at IBM Research Bengaluru in EGL. And basically, this is what is coming to your doorstep. So it's a dream that you guys will be having access to this. And the fact that, this kind of ecosystem is brewing here, there is so much interest for doing quantum computing. The fact that a quantum computer is going to come here. And yeah, this is basically stars aligning and basically magical things can happen if we keep up the interest and drive ourselves forward to do something good. So I have a lot of expectation, and I think this ecosystem has a lot of potential to get things going. So with on that note, let's get started with this talk. So the vision of IBM Quantum, or yeah, let me where point it is it on? Yeah. Mm,
Great. Yeah. Okay. So I wanted to talk about a more I wanted to pick a special topic for this audience, particularly because you will be having access to a real quantum computer. So this topic in particular, quantum circuit compilation, this is something very relevant and important to doing quantum computing on quantum hardware. Uh, like given the kind of discussions that go on in the community, there is a misconception that using simulators is the same as doing quantum computing, but that's not really the case. And one of the takeaways I hope we can have from this lecture is to know the difference between what it is to do real quantum computing on quantum hardware itself. So the mission of IBM is to bring useful quantum computing to the world. So, how can we do that? I will be touching a little bit upon that topic as well here. And I'd like to start with what the objectives and key takeaways for this session would be. Before that, I would like to say that for me, I'm okay with having a more informal session. If 70% of you guys are, comfortable with or comfortable and are able to take away at least 70% of the content that I'm talking about, that will make me happy. So my objective is personally is not to get to the end of the lecture, but whatever I'm covering, if you guys are able to understand that, that's more important to me. So at any point of time, if you have any questions, please feel free to put up your hand, interrupt me, and ask me any questions that you want to, ask. So for you guys, from this talk, what are my objectives in terms of the topics and what I hope will be the key takeaways are these three things. So what it means to do useful quantum computing, that will be the first one of the things that I'll be talking about. Then what it means to do quantum computing on quantum hardware and how it differs from using a simulator. Then, last but most importantly, after this lecture, you guys need to continue learning, right? So, this fest is an amazing way to kickstart this whole effort on upskilling you guys and getting you more accustomed to doing quantum computing. But the learning starts from here, and what can you, rely on to give you that learning? So, we will touch upon a few resources that you can use to upskill and equip yourself in quantum computing after this talk. So, what does it mean to do useful quantum computing? To elaborate on this, I'd like to quote Jay Gambetta, an IBM fellow and the vice president of quantum computing. At that time, he was the vice president of quantum computing when he said this, but right now he's the director of IBM research. And he said, I like to say if you're not using 100 plus qubits, you're not doing quantum. So, what does this statement mean? 100 plus qubits is a big number, right? Relatively, compared to what we see today, and what the highest number of qubits we have on, say, live quantum system as of now is with IBM with 156 qubits. So, what do we mean by that? And I'm specifically talking about superconducting qubits. So, what does this mean? Let us, analyze that statement a little bit more. So there is a rich seam of problems that cannot be solved by classical and AI superconducting, and it never will be. So these are trillion-dollar problems that quantum computing was designed to solve. So if you look at the complexity of problems, you have hard problems which are NP complete. And then you have problems which are easy for quantum computers to solve, but not really for, say, the classical computing resources. And of course, in between these two, you also have easy problems which can be solved in polynomial time, which is what we use current day classical computers for, right? So, what are these problems that quantum computing was designed to solve? So, modeling molecules, atoms, electrons, and quarks with unprecedented accuracy. So, this is basically a work which was done on the Heron quantum computer with 77 qubits using HPC, basically the superconductor Fugaku at Riken, in order to achieve results which are comparable to the best classical approximate methods in both accuracy and timing. And as you see here, it took total of 12 minutes using 77 qubits and 1.5 hours of supercomputer time to get to be able to solve this particular very complex problem. So this is that is one of the example problems that quantum and in more specifically say using methods such as quantum centric supercomputing is it these are some example problems which are expected to be useful to solve using a quantum computer. You also have initiatives for developing lighter, longer lasting batteries for electrical vehicles. Then you have designing better materials for like say planes, ships, these kind of industries. Then you have discovering basically in healthcare you have drug discovery, which is again a very active field which is hoping to benefit from quantum computing. And you also have technologies such as renewable energy. So, to kind of put this into a more rosy picture, you have easy problems. So, if I asked you to do 10 into 3, are you going to pull out a calculator or write a sophisticated Python program? No, right? It's just mental math. You can do 10 into 3. It's very simply 30. So, if I want to do these kind of simple problems, I'm not going to use a calculator or a sophisticated Python program. Same way, you don't want to solve trivial problems using a quantum computer. And very often than not, going back to Jay's statement, uh, you don't want to solve very simple problems using a quantum computer because it's an expensive resource and it can do much more than a classical computer can. If a classical computer can solve a problem well, you should use a classical computer for that. You should use a quantum computer to tackle more difficult problems that it is suitable to solve, right? So, in that sense, there is a sweet spot between very easy trivial problems where you don't need quantum computing for doing tasks like arithmetic or to build video games. So those are some easy problems for which you don't want to use a quantum computer. Then you have very hard problems as well, for which you need fault tolerant quantum computers, which means current day quantum computers are going to fall short on certain places to be able to implement uh, the more advanced quantum algorithms. So for example, if you look at Shor's algorithm or Grover's algorithm, these are algorithms which require a fault tolerant quantum computer for several reasons. Firstly, you need high fidelity in terms of the computing, which means that the result your result is of good quality and it is not too badly affected by noise. But also the algorithm itself, for example, if you take Shor's, to even factorize a very simple number, you need a high number of qubits you need a high number of qubits and you need to be able to implement gates of a higher depth. So in these cases, you need a fault tolerant computer which has a lot more which is a lot more powerful as compared to the current day quantum computers. But we are in the utility era and we are going there. So what you're looking for as to when to use a quantum computer is this sweet spot of which is in between easy problems, easy or trivial problems, and very hard problems, which are going to take some more time to solve. In terms of the hierarchy, so what are the problems that we can actually tackle? We have solvable problems, we have interesting problems, but the ones we need to aim the most for are timely problems, which means you want to pick problems that are solvable, timely, but also of interest to solve uh, using the current existing quantum computers. And depending on which field this is being implement like which field it is being applied to, its success will depend on how using a quantum computer can bring value above what classical capabilities alone can achieve. So what are some of the industries where this is expected to have an impact? We have chemistry and materials, we have optimization and search problems, we have machine learning and AI, of course, and we have numerical simulations. So these are the sort of type of problems, which fields or which industries it hopes to impact. You have aerospace, automotive, chemicals, electronics, and semiconductors. You have energy, financial services, and healthcare and life sciences, most importantly. So this is of course not an exhaustive list, but this is supposed to be representative of the wide and far reaching impact that quantum computer can have, and where we need to look for applications to do these things. So moving on from there, quantum must be performant and quantum must be easy to use. So, as we all know, quantum computing is not a very easy topic to start with because it's very multifaceted, right? You need knowledge of physics. You need knowledge of computer science. You also need knowledge of information processing, and you also need domain specific knowledge if you're looking at an application. I know this seems intimidating, but on one hand, while it is this way, if you look at it from the other side, people from computer science background can do quantum computing. People from physics background can do quantum computing. Say if there is a researcher in bioinformatics who has tried every possible avenue of research they know or that they are interested in to solve some particular protein folding problem, and they are not finding much success, and say they turn to quantum computing looking for a solution, they can also try to use quantum computing. So to make it more approachable, we need to make sure that quantum is easy to use, but we also need to make sure that it is performant so that it is actually useful. So one of the main offerings from IBM on the software side is of course Qiskit, which is I think accepted as the lingua franca of quantum SDKs. So for me also, like I think I personally in my journey I used MATLAB to write Grover's algorithm when I did my master's thesis. At that time, I think I had some I had my own understanding of what I thought quantum computing was, but it was only after I entered the industry and I came across things like Qiskit that I understood, how much more easy and how much more understandable. And you can actually use it like a proper brick or a building block to build up to what you want to implement. So in that sense, you have Qiskit, which sits in the software stack, area of quantum computing at IBM, let us say. So, but where exactly are we using Qiskit? So, to understand that, we first need to understand the anatomy of a quantum computing service. Now, this is very uniquely specific to how you implement a quantum program on a quantum computer. It's not unique to an IBM quantum computer. In general, the anatomy of any quantum computing service must have this kind of blueprint. So you have the user who uses a quantum programming language to write or say build quantum circuits. Then they send these quantum circuits using some kind of cloud service to some server in a laboratory. Okay, and this quantum circuit then kind of undergoes some runtime compilation and things like that. It goes through the control electronics and it gets converted to pulse sequences. Then these pulse sequences are what are actually implemented in a quantum computer. If we go back a few slides and I showed you this, right? This is of course a replica, but particularly the actual chip in the quantum computer is at the base. So this whole chandelier thing that you see that is golden and very shiny, that is actually part of the refrigeration equipment. It's not actually the quantum computer itself. It's just the cooling apparatus that makes the chips stay at the temperatures required to maintain superconductivity. So in that sense, coming back to this slide, right? Uh, what actually gets implemented on the quantum computer are pulse sequences. So there are these many things going on when you are implementing something on a real quantum computer. And why do you need a cloud service? Because at this point of time, you cannot have your quantum computer on your lap like you have a laptop which is built on classical, hardware. Rather, you have a quantum computer located in some place, but you are still able to use it thanks to the cloud service. And this is what this is what the anatomy of that quantum computing service looks like. Now, here specifically, what is the, where are we talking to, or what is the scope of what we are directly affecting, or where we are talking to? It is in this regime where, as a user, you build, quantum circuits or whatever, and you send it through the to the cloud service. Here, specifically, Qiskit itself will be used here just in the first step to build your quantum circuit. So for IBM, you have something called as Qiskit runtime, which performs this cloud service operation, and that is done using this SDK called as Qiskit runtime. So now, what is Qiskit? Uh, just to put a formal definition to this. So Qiskit SDK is an open source SDK for working with quantum computers at the level of extended quantum circuits, operators, and primitives. So some of the operators and the like, which was discussed in the previous session, right? If you want to actually build an algorithm with that, you will have several components. You'll have qubits which are undergoing measurement, and then you might take the expectation of some qubit states with respect to some observable. So yeah, observables. I mean, I'm not going to go into it now, but so these are things that you can do with Qiskit. So then of course you have Qiskit runtime, which is a cloud-based service for executing quantum computation on IBM quantum hardware specifically. Then you have Qiskit patterns. Now, this is not Qiskit specific, but I mean, in the sense you can apply this to a general quantum SDK. But Qiskit patterns in particular is a framework for breaking down domain specific problems into stages so that you can run it on a real quantum computer. So, if I take some problem, right, say I want to solve the protein structure prediction problem and I want to run it on a quantum computer to solve and find the structure of the molecule. How will I do that? That's such an abstract thing to think of, right? But if you break it down in this using this Qiskit patterns framework, you can actually have a stepwise plan as to how to really implement this on a quantum computer step by step and get answers from it, and get the solution that you're looking for. So what is this? We will not do a detailed breakdown, but we will look at it in some more detail in upcoming slides. Then you have the Qiskit ecosystem, which is a collective, uh, it's a collection basically of software and projects that build on or extend Qiskit. So you have things like Qiskit SDK, you have Qiskit runtime, you have Qiskit Air, and you have Qiskit add-on packages, which also form part of the Qiskit ecosystem. So to get started with Qiskit, right now you don't actually have the IBM Quantum platform itself is on IBM Cloud. If you want to, in terms of installation, you will need to install Qiskit with the visualization package, and you also need to install Qiskit IBM Runtime. And in terms of you need to have an account set up if you want to access the runtime service with a token instance and everything. So once you set that up, you are sort of ready to just start building a circuit and doing going forward. Now at this point I would like to make a remark. If you just want to test and understand how to use Qiskit, you don't necessarily need say to start in the beginning itself. You don't have to immediately implement things on quantum hardware. You can use Qiskit and Qiskit Air to just play around with the features and just understand things. But again, if you want to do useful quantum computing, at some stage you have to set up the service, because you can use the 10 free minutes to run your circuits on real quantum hardware. So for the Qiskit patterns frameworks, Qiskit patterns framework, you have 4 major steps. So you map a problem to the first one is to map your problem to quantum circuits and operators. So if I say I want to solve the protein structure prediction problem, I have to come up with a model for that problem and think about what aspects of this problem I am going to what part of this problem am I mapping to the qubits, what part of the problem becomes my observable or my Hamiltonian. So these are some things that you have to do in the very first step. Now, after you do this, the second step would be to optimize your circuits for implementing on target hardware. Now, this is why quantum circuit compilation is very important. We will come to this. As we go on, this is one of the things we'll mainly discuss. But after you optimize your circuits, the third step would be to actually execute on the target hardware. And the last step would be to post process your results and get the results back from the quantum computer. So, say to map a problem, what do we need to do? We start with a numerical representation and we map it to a quantum computing representation. After this, we choose a quantum algorithm to actually solve a problem. For example, for the protein structure prediction problem, if I map, say, the structural components or the geometry of like my molecule, say I'm picking some, lattice to be the template. I will map these structural parameters to the qubits. Then I will say that the energy of the molecule, I will build a Hamiltonian which represents the energy of the molecule. Then when I minimize this energy, I can say that the minimum energy configuration corresponds to the structure of the protein. So this can actually be solved using something called as VQE, because if you formulate it as an optimization problem, it doesn't just have to be VQE, it can be different things. But VQE is one of the algorithms that you can use. So then you choose the quantum algorithm and actually run it to solve the problem. But let's not focus on this. For me, I want to focus for this session on the first two steps. And for this, you can use in the first step, if you build any quantum circuit, right? In the second step, if you want to implement it on quantum hardware, you have to optimize your circuit. And optimizing your circuit involves quantum circuit compilation. So how is that the case? First, let's discuss very simply how you can build a circuit with quantum SDK. So these are the foundations of quantum programs, right? And these consist of operations, including gates, measurements, and resets that manipulate the state of the qubits. So anytime I want to go from, say, a problem to a solution, I want my input to encode the problem, and I want my output to represent the solution. So from how do I go from input to output? I have to evolve my quantum state. And that evolution can be done by using gates, right? And these gates, measurements, and resets, these help manipulate your qubits. So this is a very simple Bell state circuit. You have a Hadamard gate, you have a CNOT gate, then you have a barrier, then you have two measurements on each of the qubits. Now, I'm not going too much into detail on the basics itself, because I think those are covered in other sessions. But yeah, how do you actually implement the circuit? This is the code. I have skipped the installation steps here. Maybe I can show it to you in like notebook later if we have time. But to build the circuit, you first have to install Qiskit, and then you have to import quantum circuit and quantum register from the circuit. Then you build your quantum register this way. And as you see, I'm applying, say, the Hadamard gate on 0th qubit in my circuit. Then I'm implementing the CNOT gate with 0th qubit as the control and Q1 as the target. Then I'm measuring all the qubits. And this circuit.draw of MPL helps draw your circuit in a matplotlib style, which looks more nice than just giving, say, print circuit. So now let us discuss how we will optimize circuits for target hardware. Now here's where quantum circuit compilation, or more specifically the IBM term transfilation, comes into view. Let us discuss that in a little bit more detail. So, how do you optimize your circuits for implementing on hardware? There is an absolutely necessary and required condition for where you have to transpile your abstract circuit into a circuit that can run on target hardware. And then there is an optional step as well, where you can verify your circuit with simulations. Excuse me. Any questions so far? But am I for just to like? Is this a bit too? I'm trying to keep this a bit high level, or is this like whatever I've spoken so far, has that made sense, or do you have any clarifications about what has been discussed so far? Is it clear? Okay. So, but first of all, why do we need to transpile an abstract circuit? This is because real quantum hardware comes with a few constraints, and your abstract circuit needs to satisfy these constraints if you want to actually implement the circuit on your target hardware. Now, what are these constraints and where are they coming from? So, firstly, when you build a quantum computer, you cannot put every gate imaginable to be operable on that quantum computer. Instead, we have something called as a basis gate set, which contains a specific set of gates that can represent all possible quantum gates that you can come up with. And so, only a limited set of gates can be executed directly on hardware. Others will be rewritten in terms of these basis gates. So if I have a 3 qubit gate, 4 qubit gate, 5 qubit gate, which I can potentially have, I will decompose these gates in terms of 1 qubit gates and 2 qubit gates. Particularly, I will decompose them in terms of these basis gate sets. And one remarkable thing is that different types of hardware will have different set of basis gate sets. Not every kind of hardware that you are using will have the same kind of basis gate set. For example, some Eagle architectures which existed, Eagle architecture refers to some IBM quantum devices which used to have 127 qubits. Um, these used to have ECR gates, which are a kind of 2 qubit gate in their basis gate set. Now, the IBM quantum system 2 that we saw, these are based on Heron architecture, and these will have CZ gates. They don't have ECR gates. So that's just an example of how. Now I will show again in further slides the difference as well. But yeah, so the kind of gates that are there in your circuit, ultimately when you're running them, has to match the basis gate set of the architecture of the quantum device that you're running on. Now, after this, there's a more tricky kind of problem with in terms of qubit connectivity. Now, when I'm writing this circuit, right, here I've put Q0 and Q1, which is the 0th qubit and the first qubit. But I can also potentially make a 120 qubit circuit and say that I want to put a CNOT gate between the first qubit and the 120th qubit. Now, this is just me writing some gate, right? But how will I actually implement this? If I want to put a CNOT gate between the first qubit and the 120th qubit, how will I actually make it happen? So if you look at here, this, I'm just zooming in a little bit. So this represents basically the structure of what your quantum computer looks like. This is particularly called as the coupling map. Okay. So this shows which qubits are connected to each other. I think it is intuitive, but we don't really think about this fact that not every qubit in your quantum computer is connected to each other. So some have specific neighbors and others are not really connected. And so if I have to implement a CNOT between, say, the 0th qubit and the 120th qubit, how am I actually going to make it happen? So one way we do this is to firstly pick the layout of my circuit itself. Layout here refers to if I start with say 120 qubits, it's not compulsory that I have to always map the 0th qubit of again, a couple more terms to introduce here. We have something called as an abstract circuit or a virtual circuit, and we have something called as a physical circuit. An abstract of virtual circuit refers to a circuit which you just write using, say, Qiskit. But a physical circuit is one which has something called as a layout, and it is something that actually is implemented on a quantum computer. So you can, so to form a layout, you can map the 0th qubit of your quantum circuit to say the 10th qubit in the hardware itself. So this is I mean, yeah, so this represents the layout of a quantum circuit. And to circumvent this qubit connectivity problem, one thing we do is to firstly pick a layout itself, which will facilitate, applying a 2-qubit gate. Now, one more thing here is that because this connectivity constraint is there, you cannot directly implement a 2-qubit gate between every possible qubit. Based on the hardware you have, you can only implement it on certain, implement it across certain pairs. Okay, but the way we work around this is to implement swap gates. So say I cannot, directly put a 2-qubit gate between 0 and 120. I will keep swapping 120 with, its different neighbors by applying a swap gate until, I reach a neighbor, and until I can swap that 120 qubit with a neighbor of the 0th qubit. This is a crude explanation, but what we are doing is going to be inserting swap gates similarly, right? Until you can actually implement the gate. Then we implement the gate and do the computation accordingly. Now, aside from this, the other constraint that you have to consider is the error. Now, in a quantum computer, not every qubit is going to be at 100% quality, right? Some days, due to some calibration errors, one particular qubit may malfunction. Now, if I'm running a 10 qubit circuit, there's no necessity that I map my 10 qubits to 10 faulty or error filled noisy qubits. I can map it to the best quality qubits available based on the qubit connectivity constraint, right? So, in that sense, you also want to optimize your circuit so that it kind of tries to avoid these noisy qubits. That was a lot of explanation. So let us take look at some illustrations. If you see, like, so this is a very sort of like, this is a very direct kind of view of what a quantum computer can look like. But if you actually look at its structure, it looks something like this. So you have 0 connected to the first qubit, then to the second qubit, third qubit, but you don't see any connection between 0 and 3, right? So if I want to implement a 2-qubit gate across 0 and 3, there are some tricks that I'll have to employ to be actually able to do that. And furthermore, you see, not all are colored the same way. Some are darker in color, and some are more purple, and some are very light. So the very light colored qubits are very noisy. So in representatively, and the dark colored qubits are they have good quality. So yeah, this is just a representation of what. And aside from this, you also have the fidelity of the gates that you have in between, right? Not every 2-qubit gate connection also needs to be good. It can differ across the board. So this is what physically, looking at like a quantum computer on a program can look like. And very often, at least for transpilation, all this data is encoded using a programming object called as target. Yeah, so this is a more advanced concept, but so I will kind of just talk about it on a high level. But again, coming back to representatively talking about things, right? So, um, to have a more realistic understanding of what we mean by hardware constraints, let us take an example circuit. Okay, so this is Hadamard, and then I have 3 C0 gates. This doesn't represent anything. This is just like a random circuit that I came up with. Okay, then I have a NOT gate on the 4th qubit, and then I have an RZZ gate on the 3rd and 4th qubit. Now, yeah, this is a 2-qubit rotation gate in some sense. So if I want to implement this on, now this is just my abstract or virtual circuit. But depending on the hardware I'm implementing on, this is what the circuits can look like. As you see here, you have X gate, which was there in your previous like diagram also. Then you have RZ and square root of X gate. But then you have C0 gates for 2-qubit gates here, right? And this is for another different backend. And here I have ECR gates for my 2-qubit gates. And I have more RZ, I have square root of X, I have one X gate, yeah, and so on. Now, this is another sort of, again, like, this is another decomposition of the same circuit. As you can see, still has ECR gates, but in this case, there are several more qubits or several more gates, sorry, not qubits, several more gates which are required on this circuit as compared to this, right? And again, this is another different decomposition of the same circuit. And as you can see here, this is the CZ gate. And again, this decomposition is looking different. But this circuit and all these four different circuits, they are all equivalent. They are just rewritten in different ways. Now, if you see here, there is a Q4 and an arrow to 56, Q3 and an arrow to 57. So this is what I mean by the layout or the physical layout of a or the layout of a physical circuit. This represents the mapping of your qubit to qubits on the hardware itself. So what this means is that the fourth qubit on that abstract circuit is mapped to the 56th qubit on the device, third to 57th, 0th to 58th, and so on. So yeah, if you see here, like you can see the virtual like circuit qubits and the qubit on the hardware that they get mapped to. And here you see 0th is mapped to third, 1 is mapped to 2. So the order isn't really necessarily strict, right? But again, as I'm emphasizing that all these circuits are equivalent. So what is the difference between these four circuits and why do they look different? Now, the first circuit has been transpiled on IBM Hanoi, which is a 27 qubit device, I think. So, it's an old retired device, it's no longer online. But if you look at the basis gate set of IBM Hanoi, it has C0 gates and some of the other gates that you're seeing here. So, that is why when we had to implement this circuit, it got decomposed into this particular pattern. Now, this is again this the second and third are both transpiled actually on IBM Brisbane. So that is an Eagle device. But if you look at the starting layout which we gave here, it has 58, 59, 71, 56, and 57. And here the layout is 0, 1, 2, 3, 4, which is a trivial layout. Okay. And the thing is, as you can see, the trivial layout requires a lot more quantum gates to be implemented as compared to this particular layout. So it's always good to use lesser number of gates when you're implementing a quantum circuit than more. So in that sense, here by just changing the layout, you're able to use lot less number of gates to implement this quantum circuit. So then finally, this is a circuit which is transpiled on IBM Fez, which is a Heron device, and it is an IBM. It is it is the kind of like device that will end up coming here, coming to Amaravati. So here, if you see, you have CZ gates in the basis gate architecture set. Sorry, you have CZ gates here, and the reason for that is because in the basis gate set of IBM Fez, you have CZ gates as the 2 qubit gates, and in the previous case, you had ECR gates for 2 qubit gates in IBM Brisbane. So that is essentially why this is looking different. So now to further build on this topic, if you look at these two cases, now why are they different? One of the reasons is because if there is no physical connectivity between 2 qubits, but I am putting a 2 qubit gate between them, I'll have to add additional swap gates to make it possible. So, yeah, this is something we discussed earlier on also, right? So the solution in these cases to if I have to apply a gate between qubits without connectivity at hardware level, it's to apply as many swap gates as needed to move the qubit state, implement the operation, and revert the state back. So say yeah, this is just a simple, C0 gate run. Yeah, so this is a simple C0 gate run on a simulator, but I'm using a specific backend, and this is just to show if I have to implement a C0 between 0 and 2, where there is no connectivity between 0 and 2, then I'll have to swap 1 and 2, implement the C0, and then swap it back. So if you see here, these two are the same, but implementing this will be a lot more expensive than implementing this. So that's the idea. You can implement these swap gates as discussed here, but it's going to be expensive to do so. The reason for that is one swap gate on, say, this is on a IBM Hanoi like architecture, that one swap gate is equivalent to 3 C0 gates. and 3 CNOT gates on say a Heron is equivalent to this circuit, and on Eagle it is equivalent to this. This is just a single swap gate, right? So you can see how expensive this can get. So that is why as you implement it, you want to minimize the number of swaps. Now, this whole optimizing the circuits to run on hardware is looking super complicated and very kind of involved, right? That is why we have, yeah, so this is just again representing that this is transpiled on Eagle and this is transpiled on Heron. So the challenge is to run an abstract circuit on a specific quantum device. The solution is to do transpilation or quantum circuit compilation, where you convert an abstract circuit into an ISA or an instruction set architecture circuit. So if you have a simple Hadamard and a C0 and then a reversed C0, the transpiled circuit is going to look something like this. It will have a physical layout. It will be decomposed into the basis gate set of the device, and it will also be optimized such that you are implementing as less gates as possible. So how do you actually write the transpilation? It's very simple. Once you have the circuit ready, you have to initiate a backend. Backend is a sort of, it's the representation of the device which you want to run your circuit on. So you get the device you want to run it on using the Qiskit runtime service. Then you initiate a pass manager object. Then you use something called as a with using basically generate preset pass manager, which is a which creates a default or or a very simple sort of pre-made pass manager to transpile your quantum circuit. So use generate preset pass manager, set an optimization level. We will talk more about this parameter on upcoming slides. You pass the backend argument and it will transpile the circuit for you. Basically, you say ISA circuit is equal to pass manager dot run of circuit, and you get the output ISA circuit as the transpiled circuit. Now this is ready to be implemented on quantum hardware. Now, the reason again I chose this topic is because any circuit that you're going to come up with for any algorithm is going to have to absolutely go through this step if you want to run it on a quantum hardware. So what are the stages? So since there's so many steps involved, we can come up with a more we can come up with a way of implementing it in a planned manner. So talking about transpiler stages, you have initialization. You have the first step, initialization. Then you have layout, routing, translation, optimization, and scheduling. Now, what are each of these first steps? Initialization is to prepare your circuit for transpilation. So say if I have a 4 qubit gate or a 5 qubit gate, you right away know that you cannot directly implement this because in general the basis gate architecture set of a quantum computer is only going to have single qubit and 2 qubit gates. So if you see anything more than a 2 qubit gate, the first step you will do is to decompose that into single and 2 qubit gates. So anything with 3 or more, you decompose it into 1 or 2 qubit gates in the initialization step. Then during layout, the abstract qubits will get mapped to physical qubits on the device. Then this we already spoke about, right? Then to actually make it implementable to make the 2 qubit gates implementable. Now again, further in this step is routing, where you may want to change this layout you started with to minimize the number of swaps you have to apply so that you can implement all 2 qubit gates. Now, after this will be translation, where you change all the existing gates to the basis gate set architecture of the device. Then the final step is to do optimization, where you rewrite the circuit to minimize its depth. So basically, you do things like synthesis. So for example, if I have two C0 gates, right, I implement a C0 between 0 and 1, and then another C0 between 0 and 1. This is effectively an identity operation. Basically, nothing has happened on the circuit. Now, instead of implementing this on the hardware, put a C0 and then put another C0 and see that it's going to be identity. It's better to just do like join these two in the transpilation step and make it to be identity, so that you don't have to actually implement it on the quantum hardware. So these kind of optimizations are done in the optimization step. Then you have something called as scheduling, where this is a very kind of temperamental part of the transpilation. Now temperamental not because it's not a good operation, but rather you don't use it all the time. You only specify it if you want to do some advanced tasks. So this scheduling will introduce, say, delay instructions into different qubits to control the timing at which you implement the quantum gates. Okay, so now I'm going to skip this slide because this is again more detail on each of the transpilation steps, which I've already discussed. A little bit on the pass manager. So the pass manager is, say, the unit of doing any transpilation step. It's like so if you look, so there is another thing which we call as passes. Now passes are, say, unit of doing some operations on the circuit. Okay, more specifically, it's the representation of circuit in a directed acyclic graph representation, or a DAG, which I'm not discussing here. But pass can do a specific operation on your circuit. Say here, I have a condition where I want to remove all the if I have redundant C0 gates implemented, I want to remove all redundant C0 gates. Then I can create a pass for doing that and run that on the circuit. Now, to do the entirety of the transpilation, I'll have many such passes. One will decompose all multi-qubit gates. One will, kind of pick layouts for the given circuit. So, like, if I have a collection of all of these, how will I actually run it on the circuit? That is using this pass manager. So it manages passes, right? So I'm just maximizing the diagram a bit. So you see here it says pass 1 is to unroll bases, pass 2 is to cancel redundant gates. So multiple passes can exist, and each pass does one small well-defined task. The pass manager is going to manage all the implementation of these passes one by one, and manage how the circuit evolves through the transpilation process. And it does this by maintaining a global context about the circuit as it runs through this sort of pipeline. Okay, so I've included a source here. This is an excellent video, and it's one of the more advanced, lookups on transpilation. Now, this is going to be at a more lower level than what I'm talking about today. But it's, if you're interested to learn this in more detail, this is an excellent resource. Okay. Now, some key concepts to keep in mind here are, DAG, which I mentioned, directed acyclic graph notation. Now, I'm not covering all of these because they are all, programmatic and a bit more lower level than or more detailed discussion than what I wanted to touch upon today. But you have the directed acyclic graph. Then you have something called as a coupling map. This coupling map tells which qubits are connected to each other in your backend. And again, the third one is a backend. Backend is the data which represents all the information about the quantum computer that you are running your experiment on. Which qubit is noisy, which two qubits are connected, how long does it take to implement, say, a CX gate, or say a CZ gate on this across these two qubit pairs. So all this kind of information, right? So target, okay. So backend and target. Backend contains some of the more hard-coded information. Target contains information that the transpiler needs. Okay, so yeah, so the instructions, the timings, the error rates, these are encoded in the target rather than the backend. So that is, I know I'm kind of, it may seem like I'm throwing some jargon here, but just stay with me. And then we discussed briefly about passes and pass managers. There's also something called as a staged pass manager, which you can look into. Then you have different transpiler stages, of course, which I just touched upon but didn't talk deeply about. You can learn about each of these in more detail because there are specific algorithms to do different tasks in these transpiler stages, right? So, for example, for layout and routing, we have an algorithm called as Saber. Then for optimization, we have 1 qubit peephole optimization and 2 qubit peephole optimization for reducing 2 qubit gate depth. So there are several. Then for layout, you have something called VF2, which looks at subgraph isomorphisms. So yeah, there are a lot of algorithms which come in here also. Now, briefly touching upon these, what happens at, sorry. Okay, so I'm just briefly going to touch upon this optimization parameter level alone. So if you remember here, I said you have to set an optimization level, right? So if I here it can take values 0, 1, 2, 3. Now, what is the difference between setting 0, 1, 2, or 3? That alone I will discuss. Okay. So if you set to 0, what happens? So no optimization is happening here, but it is only like making the circuit ready with the minimal requirements for making it run on hardware, and that is done via basis translation. What is basis translation? Basically translating all the gates in your circuit to match with the basis gate set architecture of your circuit. So that is called as basis translation. Then you have minimal again layout or routing, which is done using the trivial layout, where if you have put 0, 1, 2, 3 qubits, it will be mapped to 0, 1, 2, 3 physical qubits. And of course, if this is a sort of very minimal work on layout, you have to put more swaps to make the gates work. If there are gates in the circuit which connect unconnected qubits on your backend. So this is what happens at optimization level 0. At level 1, you have very light optimization, where for layout routing, you put in a little bit more of effort. So you attempt to do it with trivial layout, and if additional swaps are required, you use some saber swap methods, and then use some VF2 post layout to select the best qubits in the graph. Then you do something called as inverse cancellation, where say if I have two C naughts, or if I have an like a gate and its inverse, I will cancel those two gates instead of implementing them on the quantum computer and doing a null operation. Then you just do 1 qubit gate optimization. Then at level 2, you do medium optimization, where you have some more, advanced, layout routing mechanisms, and you have uh, additional optimization steps called as commutative cancellation. Then at the higher optimization level, you have further more steps to optimize your circuit more heavily. I'm skipping these details because it's going to be a bit of jargon, but basically the level 3, you do very high amount of optimization compared to level 0, 1, or 2. Then some additional tools for transpilation. You can use the Qiskit transpiler service. But aside from this, you have things in the Qiskit ecosystem as well. You have things like the circuit netting toolbox. And aside from this, you can also write your own transpiler plugins. If you want your circuit to be implemented on the hardware in a specific way, you can write your own transpiler plugin as well. Okay, so now we are back to where we started, where we spoke about how to optimize your circuits for implementation on hardware. And an optional step was to verify your circuit with simulation, right? Again, we emphasize a lot that you are not using a simulator to do quantum computing, but to verify some things about your circuit and to see if it is ready for implementing on quantum hardware. While it is expensive to implement on quantum hardware and you have simulators for free, you don't do any real quantum computing with simulators because they are still pseudo random and based on classical architecture, right? So so if I want to say the problem specifically with using simulators again is that the runtime cost of simulating these quantum circuits will scale exponentially with the number of qubits. So for if I go at some point, if I want to go from 21 qubits on a on a classical computer versus on a quantum computer. On a quantum computer, if to go from 21 qubits to 22 qubits, I need one additional qubit. Whereas on a classical computer, I need 2 to the power 21 extra bits to go from or yeah to to go from these many circuits to sorry to go from 21 qubits to 22 qubits to represent on a quantum computer. I think I did the math right, but it's essentially a large number. Let's just keep that in mind. Okay. All right. So to conclude in terms of the differences, and again, one more point here, we spoke so much about transpilation. If you want to run a circuit on a simulator, you don't even have to transpile it. You can just run it like that. While it seems more simple, it also limits the scope of, what can be done on a real quantum computer, right? Because some properties, so in terms of the representation of a quantum system or a quantum state on a classical computer, it is limited as to how it's limited as compared to how you represent it on a real quantum computer. And the bigger problem is that it cannot represent the intrinsic quantum nature of quantum systems, since it's based on a classical computer. And thirdly, the practical difficulty is that it will not scale to do useful quantum computing. Now, yeah, this is just the conclusion of this part. The last part we will discuss about how you can upskill and do quantum computing. Before that, are there any questions? Please feel free to ask anything. Like, you don't have to feel inhibited. But yeah, if you have any questions, feel free to ask. Okay, so this is the last part of the talk where we are discussing how you can upskill and do quantum computing, even after this fest, and just to, or maybe as part of your career, right? So I would like to refer you all to the IBM Quantum Learning platform, where you have several courses offered for free. You have tutorials offered for free to learn the basics of quantum computing and how to solve real world problems on IBM quantum systems, like real quantum computers, and using services. So this contains things like, courses, tutorials, and educational resources by leading quantum experts. So this is what the platform looks like. And yeah, you have several courses like quantum computing in practice. You have basics of quantum information, basics of quantum algorithms. If you want to do the the simplest courses to start with, you don't understand anything about quantum computing, I'll say that you guys should start here. Okay. So aside from this, I would also like ask you guys to, be part of the IBM quantum community and interact with the IBM quantum community. Given that the fall fest is happening here, I would say that you already are part of the community. So here you have things like the IBM quantum learning platform, you have Qiskit advocates. Again, many of them are coming here for the talk itself, so there's that. Then I would implore you all to participate in Qiskit Global Summer School every year. It's great for several reasons, right? Now they have made it such that so participating in the summer school is a pipeline into becoming a Qiskit advocate now. So there's that. And really, most importantly, the latest features which are developed in a year, you will likely see something about that in the Qiskit Global Summer School. Whether it's like the latest algorithms, the latest say features like dynamic circuits, all of these will appear in the summer school. So irrespective of whether you're a student learning quantum computing, whether you're an experienced person in quantum computing, or even an employee like me, I would participate in the Qiskit Global Summer School, because it's such a great way to stay up to date with what's the latest thing happening with Qiskit. Okay. Then aside from this, you have things like the Qiskit YouTube channel, which is again a great resource. There are discussions on papers, discussions on new features, how you can use, something like how you can use the latest features to do coding, etc. So then you also have the Qiskit developer certification, though I think there are some changes going on there. So yeah, just keeping that aside for now. So apart from this, there's also the IBM Quantum internship, so IBM Quantum summer internship program, which where you get to work across the entire IBM Quantum team, from programming to materials research on real projects that matter. And the applications are open now, I think, and they're open in the fall and continue through the winter for different roles globally. So if you guys, yeah, this is just a picture of us with the interns from this year. Uh, so yeah, like I would ask you guys to apply for the internship program, learn on the IBM Quantum platform, be a part of the IBM Quantum community. And again, not pictured here, but Qiskit is open source, right? Qiskit is open source. Qiskit runtime is open source. Even if you're not starting contributions like be in the beginning itself, I would really ask you guys to upskill more in languages like Rust. I don't know if you are aware of this, but like a lot of the functionality of what goes on under the hood in Qiskit is being transferred from Python to Rust because Rust is more efficient and performant in terms of it's more performant and efficient as compared to Python for what is needed to create a quantum SDK. So upskill yourselves in Rust and learn about how open source contribution workflows happen, how GitHub works. These are all some things that you can learn today and learn right now to equip yourself so that in the future you can, apply for, say, quantum software developer roles. This is not just going to be useful for you if you want to apply to IBM, but to any, quantum software developer role that might be open across the globe, right? So yeah, I have looking at the kind of interest that is there in this ecosystem. I have a lot of expectations and hopes for this place in particular. So thank you for your attention. Thank you for being here. Thank you for having the Qiskit Fall Fest. Thanks to my other co-speakers as well for being here. And thank you all. Finally, any questions? Okay.
Hello. Ma'am,
Yeah.
actually, I got a question.
Yes.
My question is from the initial steps actually.
Okay.
So you actually mentioned to predict the protein structure, it is required 77 qubits and 12 minutes of time and
Right.
1.5 supercomputing time,
Yeah.
right?
Yeah.
And even after using 77 qubits, we only able to get the output as unprecedented accuracy. So my question is, why do we only use 77? Is the 77 qubit figure is the maximum that we can use, or like only available qubits are the 77 to get the unprecedented accuracy?
No, no. So this is a very problem specific thing. Okay. So I was
Yes.
just referring to the work that was done as part of a specific paper. So you can look at this. This is this is the work from Riken in collaboration with IBM Quantum. Based on this algorithm called as sampling based quantum diagonalization SQD. So yeah, so this is again like a ground state solver sort of use case where they are using SQD to solve the ground state of that molecule which was represented, and for that they needed only 77 qubits. Okay, so it's more like that particular problem which they picked needed only that much amount of qubits and resources specifically. So if you want the details, I would refer you to ask you to go back to that paper and read through the details, because that will clarify, I think, the specific questions that you're asking, why these many are being used and the like. So if you're using a different molecule, you'll need different number of qubits. So yeah, it'll vary a little bit across the board based on that.
So if I directly use more number of qubits than the required amount, I'll be getting the most
No,
accurate.
it is as many required. I wouldn't say it's
Okay.
more than what is needed. It's, yeah, to allocate. So in general itself, you want to, unless you're having some kind of an ancilla or whatever, you're going to be using only the kind for your particular problem. You will be using, at least in your problem mapping, you will be using only the number of qubits that you need. So okay, I can give you a trickier answer. The thing, but like simply answering it is that for your problem, you only need to use how many ever qubits you need. But when you transpile, you will your transpile circuit will have all 127 qubits. However, they will be idle because they're not doing anything, right? So if you, so part of transpiling your circuit is, and the requirement of an ISA is that it needs to match, your circuit needs to match the number of qubits which are there on the back end, because you cannot, if you have a 127 qubit device, it's not a 127 qubit device if you're only running 66 qubits, like switching on or something. That can't happen, right? You'll have all 127 qubits. Some will be idle, some will like have the computations going on. So in that sense, Do we use only the qubits we need while mapping or encoding a problem onto a quantum circuit running on a quantum computer? Absolutely yes. Shortly, that's the answer.
Okay, ma'am. Thank you.
Any other questions? Okay.
Ma'am, whatever the transpilation you're talking about is automatic or you recommend manual transpilation?
Oh, that's an excellent question. You will want to do manual transpilation if you need to do it. Okay, say I'm coming up with a different method to say I come up with a new novel algorithm to efficiently map my qubits onto the hardware, right? So basically, say I'm coming up with a new novel layout finding mechanism. Then I will have to write my custom. I can write a custom pass where I'm just using the layout part using my my pass. I'm doing the layout part of the transpilation using my pass, and the rest of it can be using Qiskit's default mechanism, right? So you want to do manual transpilation for specific tasks. Otherwise, you can just use the pre-built one because that gives you like help on what you need. But say other things like if your circuit is very going to be very heavy for how many C knots are there, then you can optionally say just run the C knot like say a commutative cancellation step. You can run that multiple times to optimize your circuit more heavily for doing that particular task. So the way the transpiler architecture is built, it's very supportive if you want to do it manually and have fine grained control over different steps of the transpilation process. But if you're just like, I don't care about transpilation, I just want my circuit to run on hardware, you just use the generate preset pass manager to come up with your sort of default pass manager, which yeah, and even there you have some knobs, right? Do minimal optimization, do maximum optimization. So yeah, by that way you can just use that if the scenario is the latter. Yeah. Thank you for your question.
Ma'am, quantum computing is mainly focuses on better optimization and simulation, right, ma'am? Yeah.
Simulation and optimization are two key areas where we are looking at quantum advantage or benefit in using quantum computing. So part of that is when Feynman first thought of why should we have, like when Feynman first had an inception of the idea of quantum computer, he said classical computers cannot sufficiently represent quantum mechanical nature, so I cannot simulate quantum systems on a classical computer. So perhaps if I had a quantum computer, it could better represent a quantum system than a classical computer can. So that's why simulation problems are some of the most important problems we want to approach using quantum computing, because there is a very good affinity in terms of the problem like pattern. Okay, but for optimization, the answer is a little bit different. So that you can give two answers for the optimization from the optimization point of view. One is that quantum computers or quantum computing in general can encode more hidden or more complex sort of patterns and correlations between different qubits than classical computing can. Why? Because if you just think about it intuitively, right? In a classical computer, you have bits where you have 0, 1, where they can be 0 or 1. But in a qubit, you can have something in between a 0 and a 1, right? So it can encode more information, and more information could potentially translate to more complexity. And if a problem itself by its nature is more complex, there is a better chance of that showing up in a quantum computing based approach than a classical computing based approach. So that is one of the reasons why optimization is a good problem to approach using quantum computing. The second, I think, answer where why suddenly people started solving all optimization problems using quantum computing. One of that is because of this really great paper, which I personally really like. It's called Icing Formulations of Many NP Hard Problems, where several NP hard problems are you show that like many QPO problems can be rewritten as a quadratic, like you can basically map it to an Ising Hamiltonian, and using an algorithm called VQE, and of course there are others, you can solve for these, you can minimize um, you can write it, make it into a minimization or an optimization problem, solving this Ising Hamiltonian, which corresponds to the cubo. Okay, so many graph optimization problems, the traveling salesman problem, which, for example, the protein structure prediction one which I talked about can be translated into an optimization problem. So many problems have this particular structure. So in that sense, it becomes a good sort of thing to approach, and because it's NP hard, it's hard to solve classically, and if quantum computers can solve that, we absolutely want to use that, and try to, it's one of the other avenues where quantum is doing something that classical cannot. So again, why you want to look at optimization problems.
Ma'am, another question.
Yeah.
There are a lot of GPUs and TPUs are building in the future also.
Mhm.
Is there any applications where we can't use it in the classical and can be solved in the quantum only?
Right. Okay. I'll give you two points there. First is, um, okay, so with a quantum computer, I go from 1 qubit to 2 qubit, right? In a single qubit, I can encode two states. When I increase, say, if I um, yeah, if I increase to 2 qubits, I'll have 2 to the power 2 qubits. To 3 qubits, I'll have 2 to the power 3. If I use up to n qubits, I'm encoding 2 to the power n pieces of information. Okay. And for using just normal bits, the same equivalent number of, n qubits will require 2 to the power n bits to represent that information. So it's an exponential mismatch, right? So in that sense, if I am doing something on a quantum computer and I want to do the same thing on using a QPU, like GPU, sorry, not QPU. If I want to do the same thing using a GPU or a TPU, I'll have to increase that many number of bits. I can just do that by increasing the number of cores the GPU has, or just adding more nodes or whatever. But then that is an exponential increase. Say if I have 1,000 qubit quantum computer, how many GPUs am I going to need to add just one more qubit to show the increase that just one more qubit can have? It's going to be extremely high, right? So we don't have those practical cases yet. So it's just a hypothetical against argument, but I think it's a very valid one as to why quantum computers, um, the scaling efficiency is good as compared to GPU. That is one argument again, but I said it's hypothetical. A more convincing or answer is not to say that quantum is doing something that uh, QPUs or GPUs or TPUs cannot, but rather the future of computing itself is going to be heterogeneous, which means that I'm running part of my algorithm on a quantum computer, I'm running part of my algorithm on a supercomputer, I'm running part of it on a TPU, and together with I orchestrate a workflow where I get an efficient answer using all these different modular components, as compared to running everything on just say a classical computer or just on a supercomputer, right? So in that sense, rather than asking can we do something with a quantum computer that GPUs or TPUs would never be able to, instead it's better to think of it as, let's use a QPU to do what a QPU can do well. Let's use a TPU to do what a TPU can do well. Let's use a GPU to do what a GPU can do well. Yeah.
Thank you, ma'am.
Sure. Yeah, I saw that there was a question here.
Thank you, ma'am, for solving all the questions.
Sure.
Mm, My question is, you mentioned about protein prediction. Could you please explain the flow? How to we are beginners, ma'am,
Mhm.
but we want to predict protein structure. Could you please explain the flow? How can we approach that problem?
Okay. Rather than the protein structure prediction problem, which is going to require a lot of domain specific, say, like knowledge about, say, proteins and like amino acids and everything, you could perhaps look into a graph optimization problem, which is more easy to sort of approach. So there is a tutorial which you can find in
Ma'am,
the IBM Quantum Learning platform. Sorry.
I am MBBC student, ma'am. In my PUC, I have familiar with that
Okay.
amino acids and
Oh, okay, awesome. Then I mean, I'll give you a brief answer because I have worked on protein structure prediction problem. I can answer that. So, the core. Okay, so the place we start is to consider a template lattice. So you have, say, I have a protein and I want to predict its structure. I'm going to look at it from the coarse grained perspective, where I'm treating all the amino acids as beads. Okay, so this is not going to be, you know. This is not an all atom approach, but more coarse grained bead based approach, where like the different, say, proteins like alanine, or you have those kind of modular components, right? I'm going to consider them as beads on a template lattice. Okay, and then this template lattice, I want to see whether now I'm now for one molecule, if I have a template, say a tetrahedral lattice, one molecule can go in either A, B, C, D. There are 4 sites possible, right? It can be in one of these places. So the first and second one I can fix without loss of generality. I'll just say A, B. Okay, or I can just say amino acid 1, amino acid 2.
mm,
Let us take the example of a 10 bead amino acid structure.
mm,
Okay, so now here I'm encoding, so the first and second I can fix without loss of generality, but for the third one, again, there are 4 possible sites, right? For the third, so I have A, B, C, D. Since it's a tetrahedral lattice, I can have like 4 sites possible. So now these 4 possibilities, I will, now this is a very simple encoding rather than a more complex encoding, but for each such amino acid site, um, I will use 4 qubits. Okay, I will say that it can either be, so I have 1, 2, 3, 4 possibilities. So each of this is a possible. Each possibility I'm representing using a qubit. So if my qubit is 0, that means that there is no amino acid there. If it is 1, I will say that the amino acid is there. So
okay.
per 4 qubits, you will only find one of the qubits to be 1, which represents that
One.
there is a amino acid there. Okay, so now this is the general sort of encoding for this, right? So I come up with this kind of general encoding, and now I know what my qubits represent. Now this qubit representation, I have to um, create into a variational. So if you use VQE to solve this, I'll have to create a variational template circuit for this. Okay, which I can use something called as an ansatz. So this is specific to the VQE algorithm, and it can be a bit complex, but just try to. I'll give you a very high level overview. Okay, so this whole encoding, I will create a general state, and after creating the general state, now how to decide which bead will go where. Now here the interactions will come into play, and there are also going to be constraints, right? So if I have a bead in here at this point, the same, you cannot have the next bead coming on the same position, right? So because there will be an overlap, and you cannot have that overlap. So this is a physical constraint. So these kind of physical constraints, and also when you can so there's something called as a Miyazawa Jerningen model, this, right? So there's you can have, okay, so for the protein beads, you can either use a HP model, where you consider hydrophobic or hydrophilic interactions. So that's very basic. Or you can consider Miyazawa Jerningen model, where the energies of different protein combinations, like the protein bead combinations. So yeah, now using this Miyazawa Jerningen model, you can kind of put the more interaction based constraints into picture, and using this we construct the Hamiltonian, which represents the energy of the molecule. Okay, now I will say that the structure which corresponds to the ground state is one with the minimum energy. So I will create the variational circuit which represents my randomized structure, and I will run the VQE algorithm on this state and the Hamiltonian I'm constructing, and I will minimize it using an optimizer. So a VQE workflow is you take a ansatz, which is like a circuit which represents a general state. Then you have a Hamiltonian which represents the cost function for minimization, and you will have a optimization step where you're doing the actual minimization. So I know it's a lot of okay. I'll let me give you a realistic map to understanding how you should implement a problem. I know I've given you an extremely high level overview, but first understand a variational algorithm. More like understand how a variational algorithm works. You can look at this paper called a resource efficient quantum algorithm for protein structure prediction. Okay, so this will attempt to explain to you how the encoding is done. There are several more efficient ways to do the encoding as well. You can look at just nearest neighbor interactions for the energy, for basically constructing the Hamiltonian. You can look at the nth nearest neighbor interaction. There are many sort of problem specific things that can go on here. You don't absolutely have to use a tetrahedral lattice. A tetrahedral lattice is going to give you a three-dimensional structure, but you can use a square lattice also, which will predict a two-dimensional structure, but it is any nonetheless a structure that you can predict for the molecule, right? So yeah, that is the briefest answer I can give you based on what I've covered so far or not covered even. But yeah, do you have any follow-up questions?
Please take 1 minute rest, ma'am. After that,
Sorry?
I have one more question, ma'am.
Yeah.
It will may help all of them.
Sorry?
How can we get internships, ma'am, in quantum sector?
Uh, okay, you have to apply, right? You have to look at what is the requirement of the internship. Firstly, I will say that more than anything, the mindset that is important is to think that, oh no, this is too complicated for me. I don't think I will qualify, so I'm not going to apply. Don't have that mindset, first of all. Like whatever you are capable of, try to upskill from there, but apply confidently. Okay. If you don't get in when you apply, ask the people who are hiring you for feedback and take that feedback and improve yourself. Okay, this is something that is done iteratively. But again, how you can get the internship? First you have to apply to as many as you can, and while applying you look at the requirements they have and try to kind of upskill in those areas. Firstly check the previous year's hiring and see what requirements they put there. Some of them will follow in the next year as well, right? But other requirements which they may have is to look at is to understand that you should look at what the company or like the academic place, what the research groups there, what they're doing, because they're going to hire you to do some related work, right? Probably it won't be, it could be something out of nowhere which but you will not know about that anyway, right? So you look at what they've worked on, try to keep up with all that, so that when they hire you, they see that okay, this is a person who knows what I've done. I can take them into work further on what I want to do. So yeah.
Thank you, ma'am. Thank you for your patience.
Sure.
Anyone?
Ma'am, good morning. And
Yes,
other
sir.
than protein folding, what are the scopes on life science or biotechnology, quantum?
Okay. So from like what, so there's also genome related, so RNA structure prediction. Then so basically the de novo genome assembly is one thing. Basically, wherever we can map a problem to an optimization problem, straight away that is a candidate. But aside from like the more say bioinformatics side, like work on biostatistics side, some extent it's possible where if you have some differential equation that needs to be solved, there are a lot of quantum based solutions for that as well, which are happening specifically in healthcare and life sciences. I think for disease basically. like predicting diseases, anomaly detection, right? It's in terms of QML, it is a very potent problem to look at. So anomaly detection, specifically early disease detection using, say, X-ray data and like existing health records, those kind of works are also going on. So yeah, there are too many things for me to list, but just off the top of my head, of course, there's also drug discovery, the like materials, basically the materials research, like some of that will translate here as well. What can be a good drug for this kind of disease? That sort of work. Yeah.
Okay, madam. Thank you.
Ma'am, is there any hardware circuits for designing of qubits,
Hmm?
like related to quantum computing?
Hmm?
Is there any hardware circuits designed using quantum computing, or to control qubits? Is there any hardware circuits?
Uh, okay. So I think maybe you're approaching this from with a more classical circuit design in mind, but here it works a little bit differently. The circuit design as of now that happens here is more for understanding what kind of problems can be encoded in different circuits and how can we create those circuits. Okay. And so in terms of how we build it for quantum computers, it is still at the stage where we are looking at, how do you, basically it's still at the level of a more efficient basis gate architecture set. So how can I have a set of basis gates that are going to implement with the lowest error possible, for example? So those kind of priorities are there, but in the future, a computer which does some default adder circuits, those sort of thing, it could come up in the future, but at the moment that is not sort of the priority in terms of quantum computing, as to my best knowledge.
Ma'am, I have another question too.
Yeah, sure.
You said for swap circuits, so much of circuitry is needed to be created,
Mm.
so that we can do it in hardware, like we can design a software for that in order to encode in hardware.
So swap, okay. So here right now in hardware, the reason we do swaps is because we want to be able to implement 2-qubit gates, which are originally not possible because of the structure of the device itself, right? And that is why, so depending on the layout, the number of swaps you need will be different. So that is not something you can hard code. Okay, depending on the structure of your input circuit, depending on what the layout is, depending on the gates in your circuit, the amount of swaps you would need to do will be different. In fact, it will also be different based on how your circuit gets transpiled, like in the previous stages, say in like how your 3-qubit gates, or like if you have 3 or 4 qubit gates, how they would get broken down can potentially impact this step. So there are a lot of like it's too specific to the existing parameters to be generalizable.
Thank you, ma'am.
Sure. Okay, thank you everybody. Are there any other questions? I think no, right? Okay, thank you.
On behalf of all of us, I'd like to extend a very sincere thanks to you, ma'am, for delivering such an excellent and insightful session, really. This is not just an informative session, but with the lots of patience you have handled all our questions. The questions and the interactiveness our participants have responded with is the true feedback how amazing your session is. Thank you so much, ma'am. Thanks a lot for that. And on this moment, ma'am, I would like to request you to accept our little token of gratitude and appreciation. We'd like to felicitate you for your such an amazing and extraordinary session for us today. So now I would like to call upon the head of the department of CSE, Mr. Y. Ramesh sir, and the co-convener of this fest onto the dais and the Dean Students Welfare, Dr. Ravi Gedala, and also the co-convener of the Qiskit Fall Fest onto the dais. I'd also like to request our beloved Financial Officer, Dr. C.H. Vasu sir, to come on to the dais for the felicitation. I would also cordially like to invite our Dean of Academics, Dr. Merugu Sivaramakrishna sir, to grace the dais. I'd like to call upon our Administrative Officer, Dr. Muniramakrishna sir, who are also the conveners of our Qiskit Fall Fest 2025, to felicitate Janani ma'am for her such valuable insights and such a patient lecture to all of our participants. Thank you for doing all this. We appreciate it. So confusing. I'd like to request all the faculty of the DAS and also the student organizing team to come on to the DAS. Student organizing team members, please come on to the dais. Kasim, please come on to the dais. Thank you once again, ma'am, for sharing your expertise and guiding us through these fascinating topics. And everyone, let's give a huge round of applause to show our appreciation to Janani, ma'am. And all dear participants, the QR code for the feedback form will be presented on the screen. Kindly scan the QR code and confirm your attendance as well as give your valuable feedback for the session. And after filling the feedback form, you can have your lunch break. And I would like to request you to be right back as early as possible, mostly by 1, because Gyan sir will be taking the next session of the workshop by then.